Before World War II forced nations into total war, aviation was still treated as a collection of individual aircraft. Fighters were judged by speed, bombers by payload. Reliability was discussed, but rarely treated as a strategic weapon. Donald Douglas saw the problem differently. He understood that air power only mattered if aircraft could fly continuously, land anywhere, be repaired quickly, and return to service without delay. His engineering focus was not on winning single missions, but on sustaining operations over months and years. When global war began, the Allies did not have to invent a logistics system from scratch. They already had one in the air. Douglas had built it before the shooting started. Donald Wills. Douglas was born on April 6, 1892, in Brooklyn, New York, United States. He grew up during a period when aviation did not yet exist as an industry. Mechanical engineering was still dominated by railways, shipbuilding, and early industrial machinery. His early environment did not involve aircraft or flight. It was shaped by practical engineering disciplines emerging alongside American industrial expansion. Douglas pursued formal education in engineering at the United States Naval Academy, where he graduated in 1914. His training emphasized mathematics, mechanics, materials, and system reliability, rather than experimentation or speculative design. The Naval Academy environment reinforced a discipline-focused approach to engineering, where failure carried operational consequences. This mindset would later define his work in aviation. After graduating, Douglas served briefly in the US Navy. During this period, aviation began to attract attention as a potential military tool, but it remained unreliable and dangerous. Aircraft failures were common, and flight endurance was limited. Douglas observed early aviation not as a pilot or enthusiast, but as an engineer evaluating mechanical limits and structural weaknesses. Douglas later continued his engineering education at the Massachusetts Institute of Technology, MIT, one of the leading centers for applied engineering research in the United States. At MIT, he focused on aeronautical engineering, studying airflow, structural loading, and aircraft stability. His work emphasized practical performance rather than theoretical extremes. Aircraft were analyzed as systems that had to function repeatedly under real conditions. During World War I, Douglas entered the American aviation industry as a naval aviation engineer. He worked on aircraft design and testing for military use, where reliability and manufacturability became immediate concerns. Wartime production exposed weaknesses in early aircraft designs, particularly in maintenance, durability, and operational consistency. Douglas absorbed these lessons early in his career. After the war, Douglas joined several aviation firms, including the Glenn L. Martin Company, where he worked as chief engineer. In this role, he was responsible not only for aircraft performance, but also for structural design, production feasibility, and operational feedback from users. This position placed him at the intersection of engineering theory and industrial reality. In 1921, Douglas founded the Douglas Aircraft Company. Unlike many contemporaries who pursued experimental designs, Douglas focused on building aircraft that could operate reliably over long distances and under varying conditions. His early projects reflected a systematic approach to engineering. Conservative structural margins, simplified systems, and an emphasis on ease of maintenance. Douglas believed that aviation would only become strategically important if aircraft could be trusted to fly repeatedly without failure. This belief guided his engineering decisions long before World War II. He did not design aircraft to impress with speed or novelty. He designed them to work consistently and predictably in environments where failure could not be tolerated. By the late 1920s and early 1930s, Douglas had established himself as an engineer whose priorities differed from many of his peers. He viewed aircraft not as individual machines, but as components of a larger operational system. This perspective would soon produce one of the most important aircraft designs in history, created before the war, but destined to shape it. As commercial aviation began to develop in the late 1920s, Douglas identified a critical weakness shared by most aircraft of the era. Airplanes were still treated as fragile machines, requiring constant attention and operating under narrow safety margins. Routes were short, maintenance was intensive, and schedules were unreliable. Douglas understood that aviation would never scale under these conditions. He approached the problem as a systems engineer. Aircraft were not isolated products. They were nodes in an operational chain involving pilots, mechanics, airfields, weather, and scheduling. Any design that ignored one of these factors would fail outside controlled conditions. Douglas therefore focused on structural margin, predictable handling, and mechanical simplicity. These priorities reduced failure rates and increased operational confidence. Douglas also placed strong emphasis on standardization. Components were designed to be interchangeable, repairs to be repeatable, and procedures to be consistent across fleets. This reduced dependence on specialized expertise and allowed aircraft to remain in service even when operating far from major facilities. At a time when aviation accidents were still common, this approach quietly improved safety and reliability. By the early 1930s, Douglas had established a reputation for aircraft that did not merely fly well, but flew often. Airlines valued this consistency. Military planners noticed it. Douglas's aircraft demonstrated that endurance and predictability could matter more than marginal gains in performance. This perspective would soon converge with a growing demand for long-range, high-capacity transport. The convergence occurred when Douglas began work on an aircraft intended to meet airline demands for range, payload, and reliability without sacrificing safety. The engineering decisions behind this project reflected everything Douglas had learned up to that point: conservative design margins, redundancy where necessary, and systems optimized for continuous operation. The aircraft would soon become known as the DC-3. At the time of its introduction, the DC-3 was not conceived as a military platform. It was designed as a commercial transport, capable of operating daily schedules under variable conditions. Yet its success demonstrated a broader truth. An aircraft engineered for reliability, maintainability, and endurance could be adapted to far more demanding roles than originally intended. By the mid-1930s, Douglas had unknowingly built the foundation for a logistical system that would become essential in a future global conflict. His engineering philosophy was already complete before the war began. When the demands of World War II arrived, the aircraft and the mindset required to sustain large-scale operations were already in place. When World War II began, the United States did not enter the conflict with a purpose-built global air logistics system. What it did have was an aircraft already proven in civilian service, the DC-3. Designed years before the war, the DC-3 had demonstrated something rare in aviation at the time: reliability at scale. Airlines operated it daily, across long routes, with predictable maintenance and low failure rates. This civilian success became the foundation of wartime air transport. As military requirements expanded, the DC-3 was adapted into the C-47 Skytrain. The transformation did not require radical redesign. The underlying airframe was already capable of carrying heavy loads, operating from rough airfields, and flying long distances with consistent performance. Military modifications focused on functionality rather than reinvention. Reinforced floors, larger cargo doors, stronger landing gear, and provisions for paratroop deployment. Douglas's original engineering decisions made this adaptation possible. Structural margins built into the DC-3 allowed the aircraft to carry military payloads without compromising safety. Systems were simple and accessible, enabling rapid maintenance under field conditions. The aircraft did not rely on specialized infrastructure, which allowed it to operate wherever the war demanded. The C-47 quickly became indispensable. It transported troops, equipment, fuel, ammunition, and medical supplies across multiple theatres of war. In environments where roads were unreliable or non-existent, air transport determined operational reach. Douglas's aircraft enabled armies to move faster than traditional logistics allowed. One of the most critical uses of the C-47 was airborne operations. Paratroop deployments required precise timing, reliable navigation, and aircraft capable of flying in formation under hostile conditions. The C-47 proved capable of these demands. Its predictable handling characteristics reduced formation errors, and its robustness allowed it to absorb damage and continue flying. During major operations such as the invasion of Normandy, hundreds of C-47s operated continuously. Aircraft flew multiple sorties under stress, often at night and under fire. Losses occurred, but the system as a whole remained functional. This endurance was not accidental. It was the result of an aircraft designed to operate repeatedly, not just perform impressively once. Beyond combat drops, the C-47 sustained entire campaigns through airlift. Supplies were delivered to advancing forces, wounded personnel were evacuated, and isolated units were resupplied. The aircraft's versatility reduced logistical bottlenecks and allowed commanders to plan operations that would otherwise have been impossible. Douglas's influence during the war extended beyond the aircraft itself. His approach reinforced a broader shift in military planning. Logistics was no longer treated as a secondary concern. It became a central factor in operational design. Aircraft that could fly reliably every day multiplied the effectiveness of combat units without firing a shot. By the middle of the war, the C-47 was everywhere. Europe, the Pacific, North Africa, and Asia all depended on it. The aircraft rarely appeared in headlines or propaganda. Its role was quiet, but constant. It moved what needed to be moved when it needed to arrive. The success of the C-47 confirmed Douglas's core belief. Air power was not defined only by fighters and bombers. It depended on systems that sustained operations over time. By designing an aircraft that could support continuous use under harsh conditions, Douglas had shaped the war before battles were even planned. Donald Douglas's influence did not end with the operational success of the C-47 during World War II. The war confirmed a principle he had applied long before it began. Aviation power depends on continuity. Aircraft must fly repeatedly, be repaired quickly, and remain predictable under stress. When the conflict ended, these lessons did not disappear. They became the foundation of post-war aviation. After 1945, military and civilian aviation entered a period of rapid expansion. Aircraft grew larger, faster, and more complex. Despite these changes, the core constraints Douglas had addressed during the interwar years remained unchanged. Range, reliability, maintenance burden, and operational availability continued to define whether aircraft systems succeeded or failed. Douglas's approach proved adaptable to this new environment. The Douglas Aircraft Company transitioned into the jet age while preserving the same engineering priorities. New designs incorporated higher speeds and advanced propulsion, but they did not abandon conservative structural margins or system simplicity. Douglas's influence ensured that aircraft were evaluated not only by performance metrics, but by how they behaved across sustained operations. The logistical mindset Douglas helped establish reshaped military planning. Airlift was no longer an improvised solution. It became a permanent capability integrated into strategic doctrine. Commanders planned operations assuming that men and material could be moved rapidly and reliably by air. This assumption had been validated during the war by the C-47 and its supporting infrastructure. Douglas's philosophy also influenced commercial aviation. Airlines adopted the same criteria that had proven decisive in wartime: schedule reliability, ease of maintenance, and fleet standardization. Aircraft were selected based on their ability to operate continuously rather than impress in isolated demonstrations. This continuity between military and civilian aviation reinforced Douglas's legacy beyond the battlefield. Importantly, Douglas did not frame his work in terms of innovation for its own sake. He did not pursue radical configurations unless they addressed a clear operational need. His designs reflected restraint. Complexity was introduced only when it produced measurable benefit. This discipline reduced failure rates and allowed systems to scale without becoming fragile. The cumulative effect of this approach became clear in the decades that followed. Modern air operations, military and civilian alike, assume a level of reliability that would have been impossible in early aviation. Aircraft are expected to fly daily, across continents, with predictable outcomes. This expectation traces directly back to the engineering standards Douglas established. Donald Douglas did not decide the outcome of individual battles. He shaped the conditions under which battles could be fought at all. By enabling continuous movement of forces and supplies, his work reduced uncertainty at the strategic level. This influence remained largely invisible, but it was decisive. By the end of his career, Douglas had demonstrated that engineering choices made in peacetime could determine wartime capability years later. His legacy lies in the systems that endured, not the moments that drew attention. In World War II and long after it, this approach proved that disciplined engineering could decide outcomes before combat ever began,